formula today and look at some consequences. Okay? So where were we last time? So, formula. Is let f of t denote the number of zeros of zeta s angle 0 less than or equal to sigma less than or equal to 1, 0 less than or equal to t less than or equal to capital T, because we choose capital T not to coincide with any ordinate of 0. Then n of t equal to t over 2 pi log t over 2 pi minus t over 2 pi plus capital O. So that is the Riemann-Kahn-Monod formula. We'll actually, when we complete the proof, we will show it's t over 2 pi log t over 2 pi minus t over pi, and then we'll get some explicit terms here. But the problem is, to bound those terms, this is the best we can do now. Montgomery, the book says, this is a result that has not been proved in over 100 years or more. I mean, this O log t. But still, some interesting things that are not known. Okay. We needed some preliminaries for this. So one of the preliminaries was what I have called theorem 1, which was something on the size of the Riemann zeta function sigma greater than or equal to 0. So it said it had two parts. For sigma greater than or equal to 1, absolute value of t greater than or equal to 1 or 2. We put 2 because of the logarithm. How do we got to put logarithm? We have the absolute value of zeta s is capital O of log t. Because of the t, I'm putting t greater than or equal to, you can put t greater than or equal to 1, in which case you would probably make it 2t or t plus 1. Okay. Part B, let 0 be less than delta, less than 1. Again, the absolute value of zeta s is capital O of t to the power 1 minus delta in 0 in delta less than or equal to sigma less than 1. And the implicit constant here, if you want, you can write this as less than c of delta. So that I don't have to write this. C of delta, which we computed, was 1 over delta, 1 minus delta, although we don't need the specific value. But one needs it, that's the value of C of delta. All right, then we had a second theorem, which was a theorem on complex functions. So that theorem was, consider a radius, big R greater than 0, and f of z analytic, and absolute z less than or equal to R. All right, I'm putting, you can put z naught. We're going to apply it with a different z naught. So, but with a loss of generality, we prove with z naught equal to 0. So f of z is analytic and z minus z naught less than or equal to R. And f of z naught is not equal to 0. And let f of z have n zeros in absolute absolute z minus z naught less than or equal to r. Suppose maximum of the absolute value of f of z in z minus z naught equal to r is m. Then the claim is that f of z naught is less than or equal to m times r over r to the power. As I said, the way we proved this was a little bit more accurate. Instead of r over r to the power of n, we had r to the capital R to the power of n in the denominator, and in the numerator we simply had the product of the absolute values of the zeros inside this disk. But since I've not listed the zeros in the statement of the theorem, we're just putting it as r over r. Okay, so we have already proved this. Now, recall what we actually did. So this is what we actually had towards the proof. Okay? So, in the proof of the theorem. Okay, so here's what we did. We first said n of t by symmetry. Well, first thing we said was we consider zeros of the c function, which coincide with the zeros of the zeta function. In the critical rectangle. Okay, so this I call as the critical rectangle. Because it's in the critical strip. All right, so the zeros of the c function and the zeta function coincide in this. The next thing we do is let script r be the rectangle 2 plus or I can put 2 minus it 2 plus it to minus 1 plus it 1 to minus 1 minus it. So we consider this as the rectangle R, and your n of t, so this is all done last time, is 1 over 4 pi times the imaginary part of the integral over this rectangle c prime of s over c of s ds. So that's what we had. And now, with g of s, and I've got to start numbering equations, so let me call it equation 1. With g of s equal to pi to the minus s over 2 gamma s over 2 zeta s, okay, we have c prime of s over c of s is equal to, now, notice that c of s is 1/2 s minus 1 g of s. So if we state that, then look at the g of s equal to this, and c of s is 1/2 s minus 1 g of s. We have c prime of s over c of s is 1 over s plus 1 over s minus 1 plus g prime of s over g of s. Okay, so we have that. And then this is obvious that the imaginary part of the integral over the rectangle of 1 over s plus 1 over s minus 1 ds is equal to 4 pi. So if you want, you can divide by 1 over 4 pi, put that as 1. Okay, so this we know that. Then, since g of s equal to g of 1 minus s, and g of s bar equal to g of s bar, we have that the integral, if you want to put 1 over 4 pi, 1 over 4 pi of the integral over rectangle of g prime of s over g of s is ds is simply 1 over 4 times the integral over a segment which we have called g of g prime of s over g of s ds, where z is this, starting at 2, going to 2 plus it, and going to half plus it. Okay, so this part is unused up to minus 1 plus it, and then coming down to, so that part is unused, so I'm just putting dots here. Okay. So this is minus 1 minus it. So we're only looking at this part. That's 1/4 of this rectangle, but we did this symmetry, s goes to s bar, s goes to 1 minus s, and so on, and then we got this. So this is number 5. So this is where we were last time. So now we're going to start with this. Okay. So we are now going to use 2. Okay. From 2. So this is where we were last time. So we're now going to start. So from 2, we get that the integral over z of g prime of s over g of s ds is equal to, so I'm taking the logarithm of this, basically, and differentiating. You think of it like that.
So why do we have the 1 over 4 pi?
1 over, this is 1 over pi. This is 4 times that. I just wrote it incorrectly. Thanks. Okay, so after I calculate this, I have to divide by pi. Okay. So the integral over z of g prime of s over g of s ds is, pretend you can take, well, actually you can take the logarithm of this. Because, so maybe I should state that at the beginning. The Riemann-Zeta function has no zeros to the right of 1 anyway. And I have drawn this vertical line to skip the zeros of the Riemann-Zeta function as well as the Xi function. The gamma function has no zeros anyway. This has no zeros anyway. So the g function has definitely no zeros on this line, which means, on this bend, which means I can put a little 2 around this and get a simply connected region where the g function has no zeros. So maybe I should start with that, okay? And each of the components of the g function. So let's say that we can enclose z by an open region, open connected, simply connected region, connected and simply connected region, in which g of s has no zeros. That means each component would have no zeros, but there are no poles there. So a single valued branch of the logarithm of GFS and the logarithm of each of these components can be defined. So the single value branch of log GFS and of each of the components can be defined in this region. In this particular region. So I can take logs and I can differentiate term by term. So thus by 2 we get, so this is the crucial thing. So thus by 2 we get G prime of S divided by G of S. So maybe we can just put integral Z G prime of S over G of S ds is the integral over Z of what? I take the logarithm of this, so it's minus S over 2 log pi. So when I differentiate, I get minus half log pi. Okay? Then here I get plus gamma prime of S over 2 over gamma of S over 2, and then I have to put another half there because of the S over 2 by the chain rule. And then I have zeta prime of S over zeta of S ds. So that's what I get. Now I'm going to estimate each one of these individually. All right? So now, clearly, oh, sorry. You should have warned me. Imaginary part. It's all imaginary part. Remember, it was for the imaginary. See, S goes to 1 minus S. That's an analytic transformation. So I have no problem there. I just do S and 1 minus S. I do the differential ds minus and so on, and I get it. S goes to S bar is not an analytic transformation. Although we are exploiting the symmetry, G of S bar equal to G of S bar. So the way I did it was to simply compare this being a dt integral and this being a d sigma integral, and just treated it as a regular Riemann integral and said that the two are equal without viewing it as an analytic transformation. Okay, so that's why I need the imaginary part. So all of this with the imaginary part. Okay, so I have the imaginary part there. So now clearly, if you look at the imaginary part of the integral over z of minus 1/2 log pi ds, the minus 1/2 log pi comes out. Okay? And what happens for the integral ds? The imaginary part here is 0, and you only have to get to the end, which has got imaginary part. We're only selecting the imaginary part. So it's minus 1/2 log pi multiplied by t. Actually, it's only up to this point. After that, nothing happens. For the imaginary part. Well, I think all right. So it's 1/2 log pi multiplied by t. All right. Now, come to this next. The imaginary part of the integral over z of 1/2 gamma prime of s over 2 gamma of s over 2 ds is equal to the log of, see, this has got an antiderivative. And the antiderivative is the logarithm of gamma of s over 2. We already said that a single value branch of the logarithm exists on this bend. Therefore, it is the logarithm of s over 2 evaluated at this point minus the logarithm of s over 2 evaluated at 2. So this is equal to the imaginary part of the logarithm of S over 2 evaluated at half, which is 1/4 plus IT over 2. That's the logarithm of S over 2 at that point, minus the logarithm of gamma 1. And the imaginary part of this. It's the imaginary part of the logarithm. So this is equal to the imaginary part of the logarithm of, gamma. Log of gamma. So the imaginary part of the logarithm of gamma of 1/4 plus IT. Okay, so that's what that is. Now at this stage, we're going to use Stirling's formula. So Colin in his lecture on the gamma function will start with a product representation of the gamma function, from which we will deduce that the gamma function has no zeros but has only poles. And then the product representation will also help us get an asymptotic formula for the gamma function, which is the Stirling formula. But here we only need the logarithmic version. But the logarithmic version is going to be pretty accurate. Okay. So at this point we say, so at this point we use Stirling's formula, which is in these in what form? The Stirling formula we're going to use is that the logarithm of the gamma of z plus alpha, I'll tell you what these are, is equal to, this is the main term, z plus alpha minus half log z minus z plus 1/2 log pi of 2 pi, and this is a crucial thing, plus capital O epsilon 1 over absolute z. So I'll explain this. 9, where alpha is bounded, so alpha is a bounded quantity, and z, so this is an estimate which is valid as z tends to infinity, but in a in the region given below. So what is this region? This is 0. So you take any ray that you like, put a 2. So z is then you're going to infinity, so we're not approaching this. But the estimate is uniform, so this means it's a uniform estimate. And this is the epsilon. So you can shrink this angle as long as you do not hit the axis. So this is the way you can think of it as Rz in absolute value is less than or equal to pi minus epsilon. So in this region, this is Stirling's formula. But notice one thing. It's an accurate formula for the logarithm because the error term is actually going to 0. The error term depends upon epsilon. So the closer you get to the poles of the gamma function, the worse off you will be. But we are not worried about this because we are on this range after IT, so we can safely apply Stirling's formula. Okay, but notice this is 1 over absolute z. That means if I exponentiate, okay, so in this region a single valued branch of the logarithm is defined because I have no problem. It's only here that I have the poles. So if I exponentiate, I'll get gamma z will be e to this expression times e to the power 1 over this. E to the power 1 over z, or 1 over absolute z, is of order of magnitude 1 plus 1 over absolute z. So it's actually an asymptotic estimate for gamma z itself. This is not an asymptotic estimate. This is an actual estimate with an error term going to 0. So this difference is actually going to 0. Okay, so note 9 yields an asymptotic estimate for gamma z, or gamma z plus alpha, whatever. All right, so that's what we have. So the celebrated formula for n factorial that we have, just write it down here, is asymptotic to e to the minus n to the power n plus half divided by square root of 2 pi. That follows from this. That divided by square root of 2 pi means, see, the logarithm of n factorial is going to be your n log n minus n. That's going to be the main term. Okay, that's what this says. But now there is n log n minus n, there is a half log n, and then there is a half log 2 pi. So you might wonder where the half log n comes, but you see, this is gamma of n plus 1. So you have to go to gamma of n, and then you will get the minus half will change to a plus half. So it'll fit. Check that this formula and that formula are really, this is a special case of this formula. Okay, gamma n being n minus 1 factorial.
Is the root 2 pi supposed to be in the denominator?
I think so. I think 1 was square root 2 pi. That's why you get minus. Oh, you mean to say 2 pi square root of. Yeah, maybe the 2 pi is on the top because of the half log. Let me quickly check. Yeah, I put a half log 2 pi here plus half log 2 pi. So I think it's e to the minus n to the n plus half, maybe times square root of 2 pi. I think I'm thinking of the Gaussian integral. So that's that half log. Okay. So now we will apply 9 with z equal to it over 2. All right? Alpha equal to 1/4. And of course, then we have to take the imaginary part. So what do we get? The imaginary part of it over 2, 1/4 minus 1/2 minus 1/4. All right? Times the logarithm of log z, it over 2. Which I will write as, okay, we'll write it that way, minus it over 2. Okay? And then you have your half log 2 pi. Don't worry about that. So it's the imaginary part of this. So that's equal to the imaginary part, it over 2 minus 1/4. Now the log of it over 2, I will write that as log of t over 2 plus the log of I. And so what is the logarithm of I? It is I pi over 4. So it's the imaginary part of that minus it over 2. And then you've got this, you can avoid this half log 2 pi and so on. So what do you end up with? Well, I get the imaginary part this way. So it's t over 2 log t over 2. I can also get the, I think I made a mistake here. You guys should have corrected this. I pi over 2. 90 degrees. Therefore, this is giving me pi over 8. And then I've got that, right? I mean, so that's separate. So imaginary part is minus t over 2. And then I've got a little plus half. It's only imaginary, so I can ignore that. So that's what we end up getting. But now I have to divide by 2 pi. Okay? So divide 10 by pi. Right? We have got a 1 over pi outside. Divide by pi. So if I divide by pi, what do I get? N of t. I have t over 2 pi log t over 2 minus t over 2 pi minus 1/8. Wait, we have to add 1. Plus, we have to add that. But I have to divide by pi. So, minus 1 over 2 pi log pi times t. So that t goes in here. So this gives me t over 2 pi log of t over 2 pi. Did I do this? Did we do this correctly? 1/2 log pi, right? 1 over 2 pi log t. So that gives me, is that correct? That if I take this and this, I end up with this? Because without the 2 pi, this is that. With the pi, it's log pi. Yeah, you get this. So minus t over 2 pi. Wait a minute, and then one other term. Plus the imaginary part of the integral over z of zeta prime of s over zeta of s ds. That to be added. So you get t over 2 pi log t over 2 pi minus t over 2 pi, and then plus 7/8 plus the integral over z of zeta prime of s over zeta of s ds plus little over 1. Don't worry about that.